right, everybody. Welcome back, Chem 11 students. Today we're talking about double displacement reactions and dancing with your mom, which is, we're going to see how that ties in a little bit. Double displacement is one of the reaction types like the previous ones that we learned about in grade 10, but we're going to go a little bit further into detail with it in this discussion today. I'm going to go over lots of examples. What you will need for this lecture, a periodic table always is helpful in chemistry, so there's my periodic table, but on the back of mine, I printed off these things. These are the solubility rules right here. I downloaded this file onto your D2L page. All right, so these are the solubility rules. What they do is they help us discern between whether something's aqueous, dissolved in water and can be a solution, or whether it is a solid, all right, insoluble in water. So these are going to help us determine states going forward through the remainder of this course. We are now going to have to come up with chemical equations, and we're going to have to be able to determine the states of both the reactants and the products. All right, so this is online. What you want to do right now is perhaps pause this lecture and get this. Either write it down onto a piece of paper or print it off if you're fortunate enough to have a printer at home that still has ink. But get this down somewhere on a piece of paper, on the back of your periodic table, or whatever it happens to be. You'll need this going forward because when I'm talking about the states of the different reactants and products, I'm going to be using this table big time. So please make sure that you have that going forward. I'll move it, I don't need it at the moment. So, a double displacement reaction involves two compounds. If you remember, a compound is two or more elements together. Now, for our reactions today, they'll pretty much always have two elements. The odd one will have three if it's one of those polyatomics are involved. But a compound always has two elements at least, and it's going to switch parts of it anyway with another compound. And we'll see what I mean in a second. The positive ions always switch with the positive ions. So here's what that means. And this is the connection to dancing with your mom. So I remember one time I was with the wife unit and we were at a family function, a wedding or something like that. And we were dancing. And I remember my parents were also dancing. So my mom and dad are here like that, they're dancing. So here's the wife unit and I, here is my parents right here. And what happened was there was a part of the song, and I'm enjoying dancing with the wife unit, right? Very good looking lady. And my parents are there and they say, hey, switch. And I'm like, switch, what are you talking about? And next thing I know, my old man had stolen the wife unit off of me. So the wife unit was now with my dad dancing. And I ended up dancing with my mom. And I remember thinking in my head, I didn't say it, but I'm thinking, that's not a fair trade. I want my wife unit back, right? Anyway, what basically happened there on the dance floor was a double displacement reaction, right? Now, if we were to treat these like ionic compounds, we know the positive ions always go first. So A would be the positive ion, B would be the negative. X would be the positive ion, Y would be the negative. And so we end up just simply switching these two positive ions. So the A and the X in this case are going to switch. So A would come over with Y. A is positive, Y as we can see is negative. And then X and B go together, and the positive ion always goes first, so X and B. So we end up with positive, negative, positive, negative. They switch partners, and we still end up with positive, negative, positive, negative. We don't end up with the two positives and the two negatives together. It's always positive and negative, because that's the force of attraction in ionic compounds. So that kind of relates back to our title there. All right. So we see that here. Here's a general reaction, same as what I had just drawn right here with A, B, and X, Y, and their switching of places. Two couples switch partners at a dance. So here are some common examples here. I have lead 2 nitrate and potassium iodide, and I can see the lead and the potassium have switched partners here. All right, and then I use my crisscrossing to make up my proper formulas. Here we have sodium sulfite and hydrochloric acid. Now, there's a metal here, and there's no metal here for it to switch places with. But remember, hydrogen is the only nonmetal that forms positive ions. So positive switches with positive, and we can see that the Na comes over to Cl, and the H goes with the SO3. And same thing here again. Sodium switches places with the hydrogen, positive ion, and we end up with water and sodium sulfate. So in grade 10, that was it. You simply, I just switched partners, use a crisscross method to make up the formulas properly, and everything was great. Not so fast, right? In grade 11, we've got to add to our understanding of that. So that's kind of like the grade 11 understanding at this point. What we're going to look at today are 3 outcomes that result from double displacement reactions. The first one is a precipitate. A precipitate is when I take 2 liquids, or a better word would be 2 fluids. A fluid can be a liquid or a gas. And so I can take 2 liquids, 2 gases, or a liquid and a gas, and I mix them together and I get a solid. So when fluids produce a solid as one of the products, that's precipitate. Neither of these had a solid going in, a solid component going into the reaction, but then a solid was formed in it, right? Now, if I go and take something like a beaker full of a fluid, and then I go and I drop like a piece of metal in there, well, the piece of metal was a solid to begin with. So I can't call it and go, look at the precipitate that was formed. No, the piece of metal was solid to start with. You have to have no solids going in and one coming out. That's a precipitate. All right? So that's one of the outcomes of a double displacement reaction, is a precipitate, a solid forming where there was no solid before. And that's where we're going to use the solubility rules as indicated in the note. All right? In the solubility rules, and we will get there, it tells you what will become a precipitate or a solid, and what will stay as a liquid or in a solution phase called aqueous, dissolved in water. We can also form a gas. So some compounds are going to switch partners, and then one of those compounds breaks down and produces a gas. And there's a really easy little way to identify that. We'll go over that when we do those examples. And then water. This one actually is not new material. These third sets of reactions are neutralization reactions. You did these in grade 10, where an acid and a base react to form water and a salt. That's a double displacement, a special type, and it produces the water. So these are neutralization reactions, this third type. So I'm going to move the iPad. Combustion reaction we're going to save for another presentation. So I'm going to move that out of the way. And we're going to go over several examples. So the first double displacement that we're going to look at are the ones that produce a precipitate. And remember, precipitate is a solid formed from 2 fluids. So we'll do several examples. This is reaction type number 1 of the double displacements. All right. We will be using our solubility rules. So I will get those out and I will refer to them as we go through the reaction. So our first example, we're going to take lead, 2 nitrate, so PbNO3, 2, and we're going to add it to potassium iodide. All right. So if we look at that, there's the beginning of the reaction here. Now, I'm going to form the products the same way we would in grade 10. So I know this is lead 2 nitrate. We figured out how to figure out shifty metal charges in class earlier this year. So lead 2 nitrate. So I'm going to get, if I switch the 2 front halves, I know that I'm going to have to switch this with this. So my products are going to be lead to iodide, which is PbI2, and potassium nitrate. And these are good formulas. I think by now we should be pretty good with formulas. So there's our skeleton equation. We haven't balanced anything off. Maybe it's already balanced, but we will check that and we'll go through it. So to balance this thing, there's one lead going in, one lead coming out. That's great. Two of these nitrate clusters. And here I only have one nitrate. Remember that 3 is part of it. So it's not 3 nitrates, it's only 1. So 2 nitrate clusters, only 1 here. So I'm going to put a 2 here. Very sloppy looking 2, but we'll live with it. So 1 lead, 2 nitrates, 2 nitrates, 1 potassium. Here I've got 2, so I'll put a 2 here and fix it. Start again. Lead, 2 nitrates, 2K, 2K, 2I, 2I. So we're balanced now, all right? So now we have to go over what the states are going to be. So I'm going to go over this sheet with you. So here are my solubility rules. And what I'm going to be looking at, the solubility rules usually focus on the second half of the compound. So the nitrate and the iodide ion here, right? So the second parts of the compound are what we're going to be focusing on for these solubility rules. So, excuse me. What we have to do is we have to know the difference between soluble and insoluble for these rules. So the first number of rules say something is soluble, and then there are exceptions to the rules, which means these things are soluble, but if I hit an exception, it becomes insoluble, the opposite of soluble. Soluble means that it is dissolved in water. And if it can dissolve in water, we say it's aqueous. Aqua, think of Aquaman, he lives in the water. Aqueous means dissolved in water. And the symbol for a solution that is aqueous is AQ. The opposite of that is insoluble. Insoluble means it will not dissolve in water. And so if it won't dissolve in water, it stays solid. I'm a solid, you can't break me down, water. I'm not dissolving in you, deal with it. So this is kind of how the rules go. The way I've divided them on the sheet, the first 5 rules say, hey, these things tend to be soluble. But if I hit one of these exceptions, they become insoluble. The bottom 6 rules say, these things tend to be insoluble, solid in water. They're not breaking down. But if I hit these exceptions, they become soluble. So that's what the exception does. It turns it the other way. So something is insoluble, but if it's with a certain thing, it switches over, and the top rules say, hey, this is soluble, it will break down in water. But if it's with these things, it becomes insoluble and it won't break down in water anymore. So that's explained on the sheet here. Be careful with the solubility rules. Now, will you have to memorize these rules? No. These will always be provided to you for any quiz or test or anything that we do going forward. I'll always have a copy of this available for you. Like I said, write them out. Very, very useful. So I'm just going to erase this and leave my rules in here to help me with this. So our first compound, and I'm hoping you can see the sheet. If not, you're reading along with the sheet or the notes that you wrote out. Like we said earlier, pause the PowerPoint if you need to, or the YouTube lecture. Our first thing is a nitrate. And here it says nitrates are soluble. That means they're aqueous. It will dissolve in water. And exceptions? There are none. Every nitrate is soluble. It's aqueous. So the state here will be AQ. And I have another nitrate over here. So it also is aqueous. That's pretty easy. The second thing, iodide, right? This iodine ion, we call it the iodide ion. It's a halide. It's a halogen, and we can see them here, F, Cl, Br, and I. Halides are things made with group 17 elements. Group 17 is your fluorine, chlorine, bromine, and iodine. So here we have it here. So a halide, they're soluble, except with silver, mercury, or lead. Well, this is not silver, mercury, or lead, so it stays soluble. This is aqueous. So I've got an aqueous solution and an aqueous solution. Now I go to this compound, the lead 2 iodide. It is a halide. Halides are soluble. Oh, so that should be aqueous, except with lead 2. So here's my exception. So this normally would be aqueous, but with lead 2, it switches and it becomes solid. This is my precipitate. Aqueous solution dissolved in water, aqueous solution dissolved in water, and here's a solid that would be formed. Neither of these is solid going in, so this lead 2 iodide is my precipitate that was formed in the reaction. All right, let's try another one. The next one we'll do is sodium, and we'll mix this with a polyatomic we haven't met yet. This is chromate. So sodium chromate and magnesium nitrate. So sodium chromate, magnesium nitrate. Again, the 2 positive ions are at the beginning and we'll switch them. So sodium ends up with NO3, and the magnesium ends up with CrO4. This has a charge of 1, so does this, so they cancel. That's a great formula. This has a charge of 2 plus, this has a charge of 2 minus, so that's a good formula. So now we simply have to see if we're balanced. We'll do the balancing here. 2 sodiums, only 1, so we'll put a 2 there. 2 sodiums, 1 chromate, 1 chromate, 1 magnesium, 2 nitrates, and 2 nitrates. So this is balanced simply with that 2. Now we're going to do the states again. All right, so I'm bringing up my rules here. And if I look, I've got nitrates here. So here's nitrate, and that's an easy one because all nitrates are soluble and there's no exceptions. So nitrates are soluble, which means they're aqueous. They will dissolve in water. So I'm taking my 2 nitrates. And after a while, you begin to actually know these things, like, oh, that's a nitrate, going to be soluble, right? Now, chromate. Chromates are down here. I include them on our table. It says chromates are insoluble. So chromates tend to be solids in water, except with ammonium. Well, that's not ammonium, that's sodium. But here it says ions of group 1. Group 1 on the periodic table are these elements here. All right, group 1. Sodium is one of those elements. So sodium breaks the rule. So the rule says chromates are insoluble, they'll be solid, but sodium is the exception. So this is aqueous. Now if we go over here, it says chromates are insoluble. This is not ammonium, and it's not a group 1 element, this is a group 2 element, so this is solid. It follows the rule. Chromates are insoluble, they're solid. So if we take these out of the way again, we can see we've got 2 aqueous solutions, no solids going in, an aqueous solution coming out, but here is our precipitate. The magnesium chromate is our precipitate. All right, and I've got one more for us in this example. So BaOH2, barium hydroxide, along with Li3PO4, lithium phosphate. These two will come together and they will form barium phosphate and lithium hydroxide. Again, I just switched the partners. The lithium came over with the hydroxide, the barium came over with the phosphate. These are all good formulas. I know how to do that now. I'm old hat at that. Now I just got to make sure we are balanced. So 1 barium, 3 bariums. So I'm going to put a big 3 here. 3 bariums, 3 bariums. 3 times 2 is 6 of these hydroxide polyatomics. Here I've only got 1, so I'm going to put a 6 here. 6 hydroxides, and 3 times 2 is 6 hydroxides. 3 lithiums, 6 lithiums. Well, to fix that, 2 times 3 is 6 lithiums and 6 lithiums. So we should be pretty good now. 3 barium, 3 barium, 3 times 2, 6 hydroxides, 6 hydroxides. 2 times 3 is 6 lithiums, 6 lithiums, 2 phosphates, 2 phosphates. So we're all balanced up. Again, if I go over the most important skills in this course, number 1, names and formulas. Putting these green formulas together, absolutely key. Number 2, balancing equations, forming and balancing equations. But again, my balancing depends on my formulas. That's why formulas are number 1 and balancing is number 2. So now the states. My rules, and I'll just read them off to you because I don't want to keep covering this over, but it says hydroxides are insoluble except with Ba, and we're with Ba here, so it becomes soluble. So this one's going to be aqueous. For phosphates, it says phosphates are insoluble but except with group 1. So this would be a solid, but lithium is in group 1. So it's not a solid, it's aqueous. If we look again quickly at the rules, phosphates are insoluble except with ammonium, that's not ammonium, or group 1. Well, this is in group 2, so the rule is going to stick. This is not an exception. So phosphates are insoluble. There is my precipitate. And then if I look again, sorry, I moved those. Hydroxides are insoluble except with group 1. Lithium is in group 1, so it becomes soluble. So here's our finished equation. Here's our 2 aqueous solutions. This is our precipitate. Each of these reactions we can see started with 2 aqueous solutions going in, and each one of them ended up with a precipitate in there. All right, so that's the first type of reaction. So if you want, you can pause the video now and write those down, and we'll move on to the next type. I'll erase these. I know you just paused the video, so it's not like I'm erasing them off the board before you have a chance to write them down. So the next type of outcome for double displacement is ones that produce a gas. All right. So these ones tend to be the trickiest ones for students. So pay attention here. These ones are the trickiest ones for students, but there is a little hitch to them, a little catch, a little cheat code you can use that I've noticed with them over and over and over again. So we'll go through our first example. We'll do 3 examples of these as well. Calcium carbonate plus HCl, hydrochloric acid. All right, so we've got calcium carbonate, a salt, and here's an acid. The acid is going to be key here, so follow that. All right, so calcium carbonate and hydrochloric acid. Again, switch my 2 front parts. Calcium will come over and go with Cl2, right? Because that's a 2, that's a 1, right? And then the H goes with the carbonate to form carbonic acid, H2CO3. So I've switched partners. I use my crisscrossing and my charges to make up the proper formulas here. And so now I'm going to quickly balance that. So if I look CaCa, CO3, CO3, H, here I've got 2, I'll put a 2 there, CaCaCO3, CO3, 2 H's, 2 H's, 2 Cl, and 2 Cl. So just that 2 is fine. And now the states, all right? So the state here is, if I use my solubility rule, that's a solid. Acids are aqueous. I talked about that earlier in the course when we were doing names and formulas. I was putting AQ after acids, saying, well, they're all aqueous. And then we have calcium chloride, which, using our solubility rules, that's aqueous. And then we have this. Now, normally we'd go, okay, well, that's an acid, sir. So that's going to be aqueous. And you're saying, wait a second, I'm supposed to produce a gas. Here's our catch. I have an acid going in and an acid coming out. The second acid breaks down into water and something else. So this actually would break down, and I would take out water. And what would be left? Well, the 2 H's went here and one of the O's. The other component would be CO2. All right? So the second acid breaks down. H2 and one of these O's goes here, and you'd be left with CO2 because one of the O's went over there. CO2. Common mistake. People will look at the water and they will put its state as aqueous, which means water is dissolved in water, which doesn't make sense. Water is a liquid in this case. But carbon dioxide, I know what that is because I breathe that out. That is a gas. And this is my gas that is produced. All right? So I have an acid that produces an acid, and that second acid breaks down. I take out the water, and I get a gas. All right? We'll do another one here. So this next one is Na2SO3 plus H3PO4. And it's going to be Na goes with your phosphate, so Na3PO4 plus H2SO3. So I just switched. The Na went with the phosphate, and the H's went with the sulfite here. I didn't put them on your list, but this sulfite is going to be aqueous if I use solubility rules. This one's sulfite is not on your solubility rules, but it would be aqueous. This is phosphoric acid. It's an acid made with phosphate, and I ate something icky, so phosphoric acid. And I'll get sodium phosphate, which, using my solubility rules, I'll see that it is aqueous. And then I think I get another acid. But again, here is that catch, right? I've got an acid forming another acid. So the second acid is going to break down. The first thing I'm always going to remove, H2O. If I take that out, 2 H's went here and one of these O's, so that will leave me with SO2. And the states of those, water, of course, is a liquid, and sulfur dioxide is a gas. So again, when you see the acid forming the acid, right, this is sulfurous acid, we break it down, remove the water, what's left is going to be your gas. All right? So you'll get partial value. Let's say I forgot that. I just stayed, kept it like this, and I stayed with my sulfurous acid. You'll get partial marks. If you take the extra step and recognize the acid forming another acid, and you break it down into water and a gas, then you're going to get full value. So pause and get these down. I'm going to erase the board, but you can always pause a YouTube video and get those down. And we'll do one more example of a double displacement that forms a gas. All right, our final example of ones that produce gas, I've got NH4Cl plus NaOH. And so I switch to two fronts. So the Na will come over with the Cl, and the ammonium comes over with the hydroxide like that. All right, I will balance this thing out. So let's see, I've got an ammonium here, NH4 here, NH4 here, Cl, Cl, Na, Na, and OH, OH. So this one's already balanced. If you make the formulas right, it's already balanced. So we'll go with the states then. The states, that's a halide. It's aqueous. This is a base. It's aqueous. Salt can dissolve in water. NaCl is common salt that you would have on food. And here we've got something that's like a base and another thing like a base. Just like before we had acid, acid, and that second acid broke down. Here we have base, base. So the second base can break down. So if we break this down, again, the first thing I'm going to remove is water. If I take H2O out of this, right? This H and that O come here, and one of these H's. That leaves me with ammonia, right? One H is gone, that O is gone, right? There's my O and one of the H. I take a second H from here, and that leaves me with NH3. And if we again, if we do the states, water is a liquid, and this is a gas. All right? So again, that's our little cheat code. Base, base, acid, acid. When we see that, look for whatever the acid or base is formed in your products to break down into water and a gas of some sort. All right? So those are three really good examples of double displacements that form a gas. All right, our third type of double displacement is the ones that form water. So now we're back to the easier stuff. That's the hardest type. If you can understand that second group, the gases, then you're doing great. Now we're doing the ones that form water. And just water, not water and a gas, just water, right? So we'll do a few examples of these. The first one, we'll take sodium hydroxide. That's my base. HCl, hydrochloric acid. And remember, these double displacements that form water, like we said previously, they're just neutralizations. You did those in grade 10. An acid and a base will give me water and a salt. In this case, the salt is actually the same formula as the salt that we would put on our food. And let's see if we're balanced. NaNaOO. 1 plus 1 is 2 H's, 2 H's, and Cl and Cl. So it's already balanced. This is good. So again, if we do the states using our solubility rules, we'll see that that's aqueous. That is aqueous. This is aqueous, but this, that's a liquid. It forms the water that we are looking for there. All right? Again, someone's going to do it. Someone's going to have water and put AQ. Oh, water is water, so AQ, because that means in water. Water isn't dissolved in water. Water is water. All right? Our next one, sulfuric acid plus potassium hydroxide. And that's going to give us, well, water. And whatever's left over, so when we switch these, a K comes over at the SO4, so K2SO4, that's my salt. And again, if we do the states, these are all, using my solubility rules, these are all aqueous. And water is a liquid. balance this, I just realized I forgot to balance it. I've got, let's see, 1K going in, 2 Ks coming out. I'll put a 2 there. H's, 2 H's, 2 H's, so 2 plus 2 H's is 4. So I will have to put a 2 here. 2 H's plus 2 H's is 4. 2 times 2 is 4 H's. Sulfate, sulfate, 2 Ks, 2 Ks, 2 O's, 2 O's. So we're all good. And our last one, our last example, barium hydroxide, BaOH, plus, a little sloppy there, nitric acid gives me, of course, water, and barium nitrate. Acid and a base give me water and a salt. And I know that all nitrates are soluble. All nitrates are soluble. This one, this is going to be soluble as well, using my solubility rules. And there's my water. It's a liquid. So in each of these, I have an acid and a base giving me water and a salt. An acid and a base giving me water and a salt. An acid and a base giving me water and a salt. And we can see the water right here. I put all the waters together in the same column, but here's your water that's produced. So what do we do now? Well, get this down into your notes, of course. You can pause the video and look at this. What we're going to do now is I loaded up and I made some corrections to it yesterday and reloaded it. So reload up the double displacement sheet. I left you a sheet on the D2L, single displacement and double displacement reactions, singles and doubles. That sheet is on your D2L. You should have already done the single displacements. Now you can do the double displacements. And what you'll have to do is form the products, balance the equation, and then do the states of all the reactants and products. All right? I'll let you know later when I'll be live and I can help you out. But I think you got this. You're pretty good with formulas. Balancing, make sure of that. And then, of course, use that solubility rules table that I gave you. And that's it. Anyway, you're off to the races. And I hope you understood everything. If not, throw a comment in the comments section of this YouTube video, or reach out to me through Edsby. Make a comment there and I can help you out. All right, I'll talk to you later. Thank you for watching, everybody. Bye-bye.